linear approximation. Alright guys, ready to do some approximating?
Sorry. Alright, so to do linear approximation, that's the same as tangent line approximation in calculus. I want to show you guys a couple of different types of questions related to this topic. Anyways, here we go. Alright, so here's our function that we're dealing with. We're supposed to write an equation to the line tangent for the line tangent to the curve at pi over 2. So here's our curve, f of x equals x plus e to the sine x. We know that equation looks like this, minus f of a equals f prime of a times x minus a. Now everything about tangent line approximation has to do with this formula setup, and so let's talk about it for a second. A is where the tangent line is. That's your x value for the point where the tangent line is for the curve, and this is your y value for the point. So this is your x, is your y, this is your slope of the tangent line. Okay, now I might reference this later. This is the approximated change. If you're ever asked, because you see, like, this is the difference in the y values, hence this is the change in the y values because they equal each other. But anyways, it's actually easier to think about it a different way. But let's just find this tangent line. So first we have to find f of a. A right now is, man, everything's tripping out here, is pi over 2. So we're going to go f of pi over 2 to see what we get. When we plug in pi over 2, we get pi over 2 right here, plus e raised to the sine of pi over 2. Pi over 2 is 1. Sine of pi over 2 is 1, so that's just going to be 1. So we have, I'm just going to write it over here, pi over 2 plus e, because it's e to the 1. And then we have f prime of a. So we have to find the derivative of f. So let's find the derivative first. F prime of x equals 1 plus, now the derivative of e to the x is just e to the x. So we just have e raised to the sine x. But I left this space right here because I know I have to take the derivative of what's inside of it, and that is cosine x. So I'm going to write cosine x right here. So we have cosine x times e raised to the sine x. That is f prime. When I plug in pi over 2 to f prime, this is what it looks like. We have 1 plus cosine of pi over 2 is 0. So it doesn't even matter what the e to the 1 is. So we just have 1. So we have 1, and we have x minus pi over 2. Yay. Okay, so here's our tangent line. Now, I'm guessing we're probably going to be using this more later, so I'm going to go ahead and simplify it now so I don't have to simplify it later. It's easier to use simplified expressions, but the great risk is that you would make a mistake in your simplification and get things wrong, so try really hard not to make a mistake. So if I add pi over 2 to both sides, those would cancel out. And if I add e to the other side, then I'd have y equals x plus e. And here is your tangent line. Now, in looking at these next two questions, it's kind of the order in which these questions are asked is kind of difficult, because you can go this way and answer this question first and then answer this question if you know that the estimated, that's the key right here, the estimated change in the f of x is approximately equal to f prime of a times x minus a. That's what it's equal to. Remember, this is what equals y minus f of a, what we stated earlier. So that would give you the estimated change. But I don't know. I feel like that's a weird way to think about it. The easier way to think about it, in my opinion, is to first find the estimated y. And then you could take the estimated y and the actual y, or the, not the actual y, but the y value at the point of tangency, and subtract those there. Let me find the estimated y first, and then I'll explain it. So to find the estimated y, we just take our tangent line, and then we plug 2 into it. So I'm going to say y, I'm going to plug in 2 into it, so 2 plus e. and this is it. This is the estimated y value. That's actually pretty simple. 2 is what we're plugging in. All right, so now going back to B and then explaining to you guys so you guys can understand it. I'm writing extra stuff right now just so you guys can understand what's going on. Now, I don't know what this function looks like. It looks kind of crazy. I'm just going to guess what it looks like. It doesn't matter. All right, so I'm just going to write a little squiggly line right there. Now, we have a tangent line at pi over 2. So we're going to put pi over 2 right here. Now, I know that pi over 2, pi is like a 3, just more than a 3. So that means 2 is slightly bigger than pi over 2. I had to change my curve there just so this works out well. So we found that the y value at pi over 2 equals pi over 2 plus e. Right? We found that earlier. And then we found our tangent line right there. Okay. Now, when we use tangent line approximation, what you're doing is instead of plugging 2 into this curve right here, the original function, we're plugging 2 into the tangent line curve so we can find this y value right here. Okay. Now, this y value is the approximated y value, which we found down here. So the approximated y value is, that's actually, I circled the wrong thing, but 2 plus e. Okay, so this is the approximated y value. This is an actual y value that we get from where the tangent line is. And this says, what is the estimated change? So you're trying to find the distance from here to here, the estimated change in the y. So all you got to do is you got to take 2 plus e, and you got to subtract from that pi divided by 2 plus e. We got to distribute that negative there. So we get negative pi over 2 minus e. The e's cancel out, and we get 2 minus pi over 2. And that is our estimated change in f of x. So this is really all you need right here to find this answer. Using this also works. If you guys take the slope, which we found earlier, which is 1, and then you plug in the a, and then you plug in the 2, you'll get this answer. This is how you find the estimated change in y. I kind of like this better though, like just finding the estimated y and then subtracting. But I'm sure there's some applications later on in math life. If you ever use it, this would be easier and more handy, and that's just making your life easier. And really quickly, I want to give you some other language. This is extra stuff, so you can fast forward this if you guys don't want it. If you guys were looking for the estimated y value, using a tangent line approximation, when you look at the tangent line, it looks like this. Okay, this is your estimated change in y. You would add this guy to both sides, and so your estimated y value would equal the estimated change plus f of a. Now, you guys know what f of a is, right? F of a is this guy right here, pi over 2 plus e in our scenario. So adding the change plus the original y value, that gets you the estimated y value. That's this guy, the estimated y value. You guys kind of see how that works? So this is the change, this is the original y value, and if you add the change to the original y value, then that's how you get your estimated y value. But you see, we found the tangent line earlier, so all this stuff is already done, and this is what we got. We got y equals x plus e. So all we had to do is plug the 2 into this, and we got our answer. If you plug the 2 into this, and this, it's the same thing. You'll get the same thing. Now let's talk about the error percentage. How would you find the error percentage? Now to find the error percentage, we're going to need to find the actual y value. So let's take that 2 and plug it in to the function, the original function. So that would be 2 plus e raised to the sine with 2 inside of it. Make sure your calculator is in radians. That 2 needs to be looked at as radians, not degrees. So hit the mode and make sure the radians is highlighted. Okay, and when you do this, you get an answer, and it's more exact. It's not the actual, it's more exact, but it still is approximated because it's a decimal. It doesn't terminate. You would get something like this: 4.482577778, depending on your calculator, how many digits your calculator is rounding it to. But this is a rounded answer. So far it's right, But 8, it could be a 7 or whatever. It's rounded off. But if you're using your calculator, just don't clear this number. Use this number all the time, and that's a more exact number than even just retyping this. It's more exact. So anyways, the way you find your error is you take the actual and you subtract from that your estimated, which is 2 plus E. Now the difference doesn't really matter if it's a positive or negative change for error analysis, because in the end you just want the percent difference, like how off is the number. So what you're going to do is you're going to put absolute value bars around the whole thing, because the percent doesn't have to be negative. This would be the difference between the actual and the estimated. So this is the error, if you will. And I guess you could say, hey, the error is negative. That means it's smaller than the actual. But it doesn't matter for the purpose that we're doing. And then you would divide this by 4.4825777. And the more that you can copy this answer, like within your calculator, not rewriting it every time, but copying it from earlier in your calculator, the better, the more exact your answer will be. This answer will be 0.0526. And when you're doing this in your calculator, don't worry about the absolute value bars. That's just saying if you get a negative in there, make it positive. And then making this into a percent, you would get 5.3%, or you could say 5.26, doesn't matter. And that's your error percentage. And we would say that our estimated change is a good estimate, because that's a pretty low percentage. Really though, depending on if it's good or bad, depends on what your scenario is. Depending on what you're working on using mathematics, sometimes 5.3% is not a small enough error percentage. So it really depends on that error. The closer that the number is to 0, the better estimate it is. And that'll be it.